Well, welcome everyone. This is the last session of this very interesting meeting. It's fully dedicated to cuprates, and we have three talks. First one by Fabio Boschini, then Bernard Keimer, and last one by Atsushi Fujimori. As in all of the sessions before, we have 20 minutes allotted for the talk itself, 10 minutes for questions. So we try to wrap up at 20 minutes, and then please mute your microphone now, and once the discussion starts, you can either raise your hand or unmute and speak up. And with this, let's get going. Please, Fabio, all yours.
Perfect. Thank you, Andrea. So first of all, thank you for inviting me. I'm very happy to have the opportunity to present a recent work we just posted on the archive 2 months ago. So first of all, I am from INRS, Institut National de la Recherche Scientifique, part of the University of Quebec. And all the measurements I'm going to show you later have been acquired by the Advanced Laser Light Source Laboratory. We are located 25 kilometers of Montreal in the nice city of Varennes. First of all, before discussing all the details of your work, I want to acknowledge the people that made this happen. In particular, Dario Armano, a PhD student in my group, with the support of Francesco Gotto, postdoc, and Nicolas Gauthier, research associate. Theory came from the Flataro Institute, and Emilis, Antoine George, and in particular, Olivier Gingras. And the BISCO sample, 2212, came from Magenda Group. So I would like to give you a general motivation and to this work. And so in this work, what we did, we used time resolution photoemission to investigate the competition between superconductivity and pseudogap. So I would like to list what we think, what I believe that we think we know about this competition, and then I'm going to offer some of what I believe are open questions. So I would say that it's pretty clear that superconductivity and pseudogap compete. Several experimental probes show that if I focus on photoemission, on ARPES, there are several ways in which we can show that they compete. For instance, we can look at the in-gap spectral weight as function of temperature. We can look at the spectral weight under the coherent peak as function of temperature. They have different temperature dependence, they have different angular dependence. So that is an indication of a competition. We can track the energy position of the spectral gap as function of temperature. It displays a non-monotonic behavior, again, indication of a competition. We can track the spectral gap as a function of a Fermi surface angle, again, showing that deviates from the D-wave symmetry, right? Again, indication of competition. However, I would like to point out that when every time we have a look at the spectral gap in photoemission, we always notice that when we compare the low temperature and the high temperature, most of the time, what we notice is that the energy position of these two peaks, right, in the superconducting pseudogap state, they're always very, very similar, right? So it's always very difficult to disentangle the two ordered parameter by just looking at the energy position of the peak. In addition, if we look at just the spectral weight, the fact that, right, the peak is the same position, and we have still these two orders at the same time present, it's always very difficult to disentangle the real mechanism underlying this competition. So this was something I wanted to stress, and I'm going to show you later how we can assess in a new way the competition between these two different orders. Another thing we know is that when we enter the superconducting state, the spectral function is particle symmetric. This has been shown more than 20 years ago in cuprates. And also we know there are several experimental evidences supporting the fact that the pseudogap is particle asymmetric. So the spectral gap doesn't have a minimum of 0, so it's asymmetric, it's not centered around the chemical potential. Okay, so based on this concept, then what we don't know? Well, if we start by looking at this prediction by cluster dynamical midfield theory from 2013 by Gall, what we realize is that in this particular case, the dashed lines show the normal state, pseudogap normal state, and then they added on top superconductivity. And what you may notice is that superconductivity tends to try to make the pseudogap particle symmetric. So once superconductivity emerges, the spectral gap tends to return back to be particle symmetric, and the coherent peaks want to emerge and be particle symmetric. So based on this, the open question is that yes, there is a pseudogap below TC probably, but what form does it take? So how is the pseudogap at low temperature when we have superconductivity? And again, coming from these predictions, how does superconductivity emerge on top of a pseudogap? And how, following this question, how does the spectral weight transfer from the two orders? And this is what we try to answer, and I believe we have very nice new experimental results supporting this. And this is a general strategy, the general scheme. So we know that in superconducting state, we have this particle symmetric density state. When we are in the pseudogap state, now this is asymmetric. So what we did is to use light to perturb the superconducting order, so just disrupt partially the long-range phase coherence of the superconducting order, and let superconducting correlation and pseudogap compete, and in real time track their dynamical competition. And in particular, this is eventually the sort of spoiler of what I'm going to show you later. What you observe only by looking at the unoccupied states is that once long-range superconducting order is disrupted, the coherent peak decreases, and the height of this coherent peak in the dark state is a measure of the competition between the two orders. So, as already mentioned, all these data have been acquired via time and aggregate photoemission spectroscopy. If you're interested, with Andrea and with Marta, we drafted this very nice review you can read, but in few words, it's a pump probe technique. We use a pump light to perturb the system, and then a delayed probe pass photometer electron. We detect photometer electron, and by doing so, we can track as a function of time how the electron distribution and the spectral function evolve on picosecond or femtosecond time scale. Now, all these measurements, as already mentioned, will be performed at the Advanced Laser Light Source Laboratory. We are a user facility, as I mentioned, in Montreal. And all these current measurements have been performed using 6 eV light, low photon energy light, and mid-infrared pump excitation. In this particular case, it was 300 millieV. If you want to have some details about the source, you can check this reference. Key aspects, we have a pretty good energy resolution for a timer solar system. So this enables us to look at these small details of the density state above the Fermi level. And also I want to mention that, again, all these measurements have been performed using 6 eV light, but we are currently upgraded the system, and now the system is operating also with high harmonics, so we have full tunability from 6 to 36 eV. Okay, so I mentioned that we measure with 6 eV, but if we have a look at all the previous timers of ARPA's work on cuprates using 6 eV, you may notice that all of them, here I'm just showing two examples, but there are many, you are mainly limited around the nodal direction. Why? Because low photon energy, so you just limit it right around the gamma point. So the point is that if we want to really to investigate the competition between the superconductivity and pseudogap, we should move towards the antinode. How can we do that? Well, my research associate, when he was a postdoc in Zier's group in 2021, showed that if you bias the sample and you accelerate all the electrons, so you focus all electrons inside the analyzer, you can extend the momentum reach without mechanically moving the sample. So this initial work done in 2021 was done using a old generation hemispheric analyzer, so without deflector technology, so we are just looking along the slit direction. However, if you extend this method and you use hemispheric analyzer with deflector technology, and here I'm just showing an archive where we indeed discuss this method, you can collect all the cone of emission in a single shot without mechanically moving the sample. And this is what we measure. So without moving the sample, now we have access to almost 90% of the pi zero direction using low photon energy light, 6 eV light. And this allows us to do very careful pump probe ARPEs without mechanically moving the sample. So we never change the interaction geometry. And this was key for this work. Okay, so now we can go towards the antinode. First of all, before showing you the results we obtain in the antinodal region, we always take a reference along the nodal direction. Why? Well, if I take this cut and I focus along the gamma y direction, and we integrated the nodal ADC momentum, we have this curve. Well, these are k-integrated nodal ADC, function of energy and delay. Why we do that? Because by doing so, we can just fit these curves with a Fermi-Dirac function and extract the transient evolution of electronic temperature. And in this particular work, we use two fluences, a low fluence where we went from around 30K to 80K, well below TC. TC of a sample that we measured, optimally up to 212 was 91K. And then we use a second fluence that we define here as high fluence, where we just went slightly above TC for alpha picosecond, but then we're always below TC. Okay, so these are the two fluences we use, 300 milliV. We know how the electronic temperature is changing, so we can use this information to remove the electronic distribution from our ARPES data and look at how the spectral function was evolving. So we went to the off-nodal cut. This again is an example of what we can measure, and the pump probe, a differential ARPES map at, if I'm not mistaken, 1 picosecond, and the near antinodal cut. So you can see we can really go close to the antinode. For the rest of the presentation, I'm gonna focus only on the off-nodal cut, but all the discussion on I'm going to do, all the figures I'm going to show are perfectly reproducible also for the near antinodal cut. And the main analysis method we used is the tomography density of state method that was proposed and demonstrated by the group of Dan Dessau. So what we do is that we take a momentum integrated ADC. So we integrate the momentum and we divide by Fermi-Dirac distribution after deconvolving the energy resolution. And this gives us direct access to the local density of state. Okay, let's have a look at these tomography density of state curves in the low fluence regime. So we selected 3 delays after the pump excitation, 0.6, 1 pico, and 3.5 pico. So let's start from negative delay, black curve, then we pump, and we clearly see that the pump excitation is filling up the superconducting gap. However, what is very nice is that we can superimpose to our data a Dines function that is commonly used to fit STS data for S-wave superconductor and is intrinsically particle symmetric. And you may notice that all our data, even when we go above the Fermi level, they're perfectly particle symmetric. Notice that we don't symmetrize, but these are our data after we remove the electron distribution contribution. In fact, this is why you notice that the energy range changes a function of a delay, because this is determined by KBT, that evolves over time, changes over time. Okay, so nothing new in the low fluence regime. We pump, we fill the gap, but it's always particle symmetric. Now we pump a bit higher in this high fluence regime. Notice again that all the delays I'm showing are the electronic temperature is below TC. What you may notice now that something strange is happening. What is happening is that our tomography density state curve deviates above the Fermi level from the particle symmetry reference. But if we wait enough time, in this particular case, 3.5 picosecond, the violet curve returns back to be particle symmetric. So we have a transient asymmetry that we observe all in the near antinodal region. Okay, before discussing the origin of this asymmetry, I want to convince you that this is a purely non-thermal effect. How can we do that? Well, I need to demonstrate that this is not induced by the electronic temperature of the sample. So, in order to do so, what we did is the following. We measured 2 fluences. What we can do is that we can select 2 delays for the 2 different fluences in which the electronic temperature is the same. So for instance, 0.5 picosecond for low fluence and 1.1 picosecond for high fluence, same electronic temperature. We can check that by looking at the momentum integrated DC along the nodal direction, perfectly superimposed. We can compare the tomographic density state, clearly different. One is symmetric, one is asymmetric. However, if we wait enough time and we go at 3 and 4 picoseconds, where the electronic temperature is only 10K below, but it's 63K, again, K integrated nodal DC, they're perfectly superimposed. We know that we have full control on the electronic temperature, but now the curves returns back to be symmetric. So this is clearly not driven by the electronic temperature. Second, how can we estimate or how can we track the evolution of this asymmetry? Well, one could do complicated fitting procedure, but the easiest possible way is to look at the ratio of the density state between positive and negative energies. If the ratio is 1, means that the curve is symmetric. If it is different than 1, it's asymmetric. And so this is what we did. And again, low fluence oscillates around 1. High fluence deviates from unity and then goes back to be symmetric after some time. Now, we don't have, so we know that we can induce this asymmetry. We know that it's delayed. We know that this is transient. We don't know exactly how we can do that. We know that the pump excitation is disrupting superconductivity. And if I compare this transient evolution of asymmetry to what we measure in the past, for instance, here, this is the gap filling that we measured when I was in Andrea's group a few years ago, or a recent work where we look at the quench of hybridization gap between main and superstructure replica in BISCO 2212 that is proportional to the phase difference of the order of the superconducting order parameter between these two different bands, so proportional to phase fluctuation. You may notice that they are all very similar in the sense that they are delayed around 1 picosecond, they last around 2 picoseconds, so very similar dynamics. What we believe is that the pump allows you to enhance the density of the fluctuation, and in this way you disrupt long-range macroscopic superconducting order for a time of few picoseconds, and this allows you, this is sort of a control knob of a superconducting order. We don't know exactly how, but we know that we can do that while maintaining the electronic temperature below TC. Okay, so this was the experimental results. Now, how did we model that? So in collaboration with Olivier, we wanted, first of all, to know how to reproduce the pseudogap state. But it can be very complicated, so we use a phenomenological model based on our experimental results. So this is how we track the pseudogap from the nodal direction to the antinode. You clearly see that we measure the pseudogap. And Olivier managed to indeed, in a phenomenological way, reproduce this dispersion of the pseudogap state using this self-energy. The only way to reproduce that we found was to have two main characteristics. The first was to impose a D-wave symmetry of the order parameter, and this allows you to capture this sort of dispersion of the leading edge of the pseudogap towards the antinode. The other way was that, at least in our experimental data, but also other experimental data in the past, right? The pseudogap is not particularly symmetric. It looks like the minimum is always located above the Fermi, it does not seem to disperse. So in order to do that, we impose a constant pole that allows you to reproduce in a reasonable way, at least a phenomenological way, the pseudogap dispersion. We know that we have a phenomenological model of the pseudogap. Now we added superconductivity, and we look at the interplay between the two orders. So we had this 4x4 Hamiltonian, plug into the green function, add the Brownian terms, and now let's see what we can simulate. Again, these are our data. This is the light-induced asymmetric density state that we see in our data. This is the particle symmetry reference, clearly different. We can superimpose the pseudogap normal state measured at 130K in the normal state, no superconducting order. And now, this is what Olivier managed to simulate, to calculate. So by using a pseudogap that reproduced pretty well our experimental pseudogap, adding superconducting correlation, you may notice that indeed, when the two orders are intertwined, you indeed can reproduce a transit asymmetric density state with the minimum at omega equals 0, so not at omega different than 0 as in the pseudo gap, but with a coherent spectral weight above a Fermi that is suppressed. When we wait enough time, again in our data, so for instance, 3.5 picosecond, when superconducting order, long-range superconducting order is recovered, we observe again the emergence of particle symmetric density state that Olivier managed to reproduce only suppressing the underlying pseudogap order. So in fact, this SC superconducting, the blue curve, is calculated by imposing that the order parameter goes to 0. As the last slide, I want to offer you a summary of all what I've discussed, or what I've been discussing. And I would say that I have 3 take-home messages based on our experimental results. First, of course, light can be used to disrupt superconductivity, maintaining an electronic temperature below Tc. This is sort of analogous. It's not exactly, of course, it's a naive way. It's similar to applying magnetic field, right? We disrupt superconductivity, staying with electronic temperature below Tc. And what we show is that pseudogap exists also below Tc when we have a short-range superconducting correlation induced by the pump excitation. And the pseudogap is clearly different than a superconducting gap, so indication that pseudogap is not a pairing gap. 2, pseudogap and superconductivity clearly compete, right? As soon as superconductivity reemerges and becomes long range, what you see is that superconductivity is competing for spectral weight and wants to impose particle symmetry. And I think that the most interesting point is the third one. As I say, when long-range superconducting order is reestablished, we see this particle symmetry as if the pseudogap was completely quenched. However, when we look at, again, there are several examples we can look at, but we know that even at low temperature, there is still evidence of the underlying pseudogap. So at low temperature, below Tc, we know that both superconductivity and pseudogap are present. We know that the density state particle symmetric. To me, that would imply that the order parameter is not 0. However, the fact that superconductivity impose this particle symmetric spectral coherent peak, to me implies that somehow superconductivity quenches the pseudogap. So the spectral weight in the pseudogap is filled up by the measure of superconductivity. And with this, I want to thank again all the people that contributed to this work, and I thank you for your attention.
Thank you, Fabio. Very interesting. Thanks so much for a nice talk. We have a few minutes for questions. Please raise your hand or unmute yourself. Anyone? I do have a couple of questions, but I'd like to wait, see if others. Let me start then, Fabio, with one question. Which is basically you're mentioning, in your last slide, so the pseudo gap is competing, is therefore not pairing. But what is it? So what is, now that you have this kind of, you have an experiment and a sort of phenomenological description based on a competition, what can you say, or what can possibly one say about the microscopic origin of the pseudo gap itself?
So in this work, we cannot say anything about the microscopic origin. In fact, all what I want to say is, right, so when we came up with this phenomenological model, we try initially to go with a pi folding with a shift of chemical potential, right? So that was more spin fluctuation induced with the gap. There was no way to reproduce the experimental data. There was absolutely no way to reproduce the experimental data. And the only way was indeed then eventually to have this constant pole and this D-wave symmetry. We cannot say, and with this current data, right, we cannot say anything about the macroscopic origin of the pseudo gap.
Can you say a little bit more then on the reason how you then sort of disqualify pairing as a pre-for pairs as a.
So first of all, because the pseudo gap you can see also here, right, in equilibrium is asymmetric. So the beam is not centroidomic equals 0. It's absolutely not centroidomic equals 0, and at least in our case, looks like there is a sort of plateau that lasts for 40, 50. We have also other measurements where we go up to 60, 70 milliV, where we see that it's sort of plateau in the antinodal region. So very difficult to compare it to a pairing gap. In addition, also in our experimental results, right, when we compare the two, this competition implies that there are two different, or this light-induced pseudogap-like density of state with minimum atomic equal zero implies that reality there are two orders that are different.
Thank you. I see that Mike has raised his hands. Mike, please go ahead.
So to answer your question, Andrea, imagine you have something like a paradensity wave state, sort of like what Patrick and Steve and all of them have suggested. Then it sort of looks like pairing, but it's also not particle hole symmetric. So there are modifications you can do, right? Say invoke things like a PDW, which would probably be consistent with this kind of data.
So I agree. So indeed, I would say that for a pair-density wave, then we impose a QD from the zero. So a center of mass that is not equal to zero. So this is not, I would say that is not compatible with preform pairs with Q equal to zero.
Right. Yeah.
Right. Then I fully agree. We don't know. Indeed, if there is this additional contribution.
Any other question? Sorry. Yeah, please go ahead.
Yeah, just since we still have a minute, just along the same line. So I guess if I have, say, something like pair density wave versus something like spin density wave as what's causing something that looks like a pseudo gap, would the same fitting procedure work in both cases? Or so I guess the question is, you are fitting this pseudo gap through this particular matrix entries in this 4x4 matrix, and
So the pseudogap again, right? So the pseudogap was a phenomenological model tailored on top of experimental data. And then once we had something that was reproducing in a reasonable way the experimental data, then we plugged this self-energy with superconducting self-energy and had a look at an effective combined self-energy to reproduce our experimental data.
Yeah.
As I mentioned, we tried to start from a spin density wave model. There was no way to reproduce this data.
I see. So you would end up with a different, I guess here you have a particular form factor and all that, and the spin density wave
was not working.
Would not yield this expression for the pseudo gap self-energy. Yeah, thank you very much.
Correct.
Right.
Correct.
I ask one more question. Sorry, one more question is, so in one of the first slides you had on the off-node data, and then you're pumping and showing how you retain a symmetric gap. Yeah, I think you went by 1 point. Yeah, this
one.
If I look at the negative delay, so T minus, shows more than T0, I do see a double peak structure, right, in the data. That I imagine is bonding antibonding splitting.
Correct.
Okay. So what happens when you go now and you pump the system and you look at delays, it then seems to disappear. Could I think in terms of, the loss of coherence we've been discussing in relation to the superconducting condensate now also manifesting itself in a loss of clear bilayer splitting as you pump your system?
No, I think it's just a single particle scattering. So it gets broadened up and you cannot resolve it. It's still under here. You can see a 3.5 pico. You see in here that there is a double sort of bump that is just very broad. It's just very, very, very broad. In fact, also you may notice
it's
that
it's not thermal broadening though down there, right?
is not thermal broadening, but you have a single particle scatter rate that is giving enough contribution. And also you may notice that indeed the low fluence and high fluence, this was just a bit of aging of the sample. But the spectral feature got a bit broadened up, and if you compare the two negative delay, they're slightly different, simply because the spectral feature was slightly broadened up, and so you see a bit less the bonding antibonding spectrum.
I see.
This is the way in which we
describe
we describe this. Yeah.
Okay. If there are no more questions, please join me in thanking Fabio again. Thanks so much.